So thank you all for joining us today for this 5th season for IGCP648 virtual seminar series. So for those who don't know me, so I'm Luc, I'm your host. And today we are having Dr. Sorry for pronunciation, so it's a Qian Yuan. That's it.
Yes,
yeah?
This helps you to pronounce this Chinese character, Qian.
Qian, yeah.
Yeah, thank you.
No worries. A Texaco, so you're a Texaco Postdoctoral Fellow at Caltech Institute of Technology in the USA. And today you will be presenting what's controlled the morphology of the Earth's basal mantle structures. And your research focus is on a dynamic process in the interior of the Earth and how these processes influence the surface of geological activities such as plate tectonics, volcanic eruption, etc. And you primarily use geodynamic simulation as well as a range of geophysical observation, petrological and geochemical analysis in pursuing in the related research on this global mantle dynamics. The audience is all yours.
Okay, thank you, Luke, for the nice introduction and also invitation. And also my great pleasure to see my friends and also new colleagues there. And okay, so the title is what controls the morphology of these Earth's basal mantle structures. So yeah, first I want to acknowledge the support I have been received in the past several years. First, my PhD advisor, Mingming Li, he's a geodynamicist, and also my committee members, Edward Ganino, he's a seismologist, and also Dan Shen, mineral physics, and also 2 geochemists, that's Rich Herwig and also Matthew Bowles, and also another mentor, Steve Dash, he's an astrophysicist. So also I get some support, already get a strong support from Caltech with my new mentors here. That's Michael Gurnis and also Paul Ismail. And also if you are interested in any part of my presentation or my research, feel free to contact me. So yeah, I want to first give some basic information about mantle convections. Because there are maybe an audience that study environment or soft earth science. So the Earth's mantle is solid, but in geological timescale, it can convex. So how? The philosophy is very similar to this cartoon, as I'm shown here. If you use fire to heat a tank of water, the bottom part will get hotter. So when it gets hotter, the density decrease, then it tends to rise. But when it go to the surface, it get colder, and then it will sink down. So this is kind of upwelling and downwelling cycles. Actually, this is very similar to the philosophy that have been shown in the mantle convection. As we know, we have cold downwelling, that's likely to be the subducted slabs. And then we have mantle plume that can rise to the surface and cause super volcanoes. So the philosophy between these things are very, very similar. So of course, if you want to know more detail of Earth's interior, you need seismic images, particularly about seismic tomographies. So this one is a classical study more than 20 years ago. So as you can see beneath the North American continent, this image shows the cross section beneath this part. As we can see, there is a linear blue structures that likely represent the subducted slab. So this is blue structures. So when you see image in seismic tomography, the blue means the velocity anomaly, the velocity speed is higher than the average or the reference velocity. So now let's see the red colors. So here is a famous tourism site that you may have heard about. That's Yellowstone. So a few years ago, there is a very good study published by Steve Grant's group. They show there is a plume-like structures rising from the core mantle boundary directly to the surface. As you can see, the radius of these plumes is larger than the typical theoretical thermal plume, but it's still kind of small and plume-like shape. So this red color means the velocity, seismic velocity is slower than the reference or slower than the background mantle. So the most two important thing in seismic tomography is blue structures and the red structures. So red means slower than the pre-model, or blue means faster. So this showed the regional study. Now let's move on the global seismic tomography. Here is study seismic cross-section of the equator, or I'm not sure it's equator. Yeah, but it's cross-section of the Earth. So the data is kind of a little bit old, but the recent data also show these features. Previously, we have shown the linear structure of the slab, and then we show plume. But if you see the large scale of the Earth's whole mantle, you will see there are two huge blobs. Yeah, that doesn't look like mantle plume, because we said the red features means maybe plume-like structures and slow anomaly. But these things are not plume-like, so they are kind of blob. Their size are comparable to the cold downwellings, yeah, or subduct slab that accumulate above the core mantle boundary. So the question is, what are these two massive red blobs? So actually, they are known in geophysics or seismology for more than 20 years ago, I think. They are more officially called large low shear velocity provinces. One is beneath the Pacific Ocean, another one is beneath the African continent. They are all above the core mantle boundary. So the shear wave anomaly within them are usually within 2% slower than the background mantle. So this shows the shear wave anomalies. But actually, these two blobs are also very obvious in global P-wave models, as shown by this review paper by Ganero like six years ago. So the yellow one shows the degree 2 structure of the shear wave anomalies, and the green one also shows similar structures, degree 2 structures. So in some literature, you will see they call them large low velocity provinces, because P-wave is also there. Yeah, but S-wave is more obvious. So in this presentation, I will call them LLSVPs. So why we care about LLSVPs? I'm aware this year IGCP have a lot of some presentation that already talk about LLSVPs, but I still think I better talk about this important insight. So this is a paper by Tosvik like 10 years ago. So it found that if you project the boundary of LLSVP to the surface, and then you do the plate reconstruction and other stuff, you will see that the boundary of the LLSVPs may control the eruptions for the large igneous provinces and also kimberlite eruptions, and also some active volcanoes at hotspots for at least the past 200 million years. They have other studies suggest that it can be even longer. But anyway, this is a long time scale. So by studying the two blobs, we can better understand the Earth's long-term thermal and chemical evolution. So then how these two blobs are formed? So I would say that right now there are still people arguing these two blobs are purely thermal. Yeah, because purely by geophysical evidence, it can be thermal. But if you consider the surface correlation and also the anti-correlation between the shear wave and the P wave at the boundaries, and also it has a very sharp boundary for the LLSVPs. So in that way, I think more people think these two blobs are dense thermochemical pile. Yeah, so if the LLSVP are dense thermochemical pile, then there are two popular explanations. One is they form by accumulation of subducted oceanic crust. This idea has been proposed almost 30 years ago by Christensen and Hoffman. Later, there are 3D work also showing that. Another increasingly more popular idea for this origin of LLSVP is that they are kind of primordial materials. So this great study by Labros, published in Nature 15 years ago, found if you initially have the basal magma motion, and when you gradually crystallize, this part can be relatively iron rich, and this can stable the piles. And in this way, you can form the LLSVPs. And also, if you have some remained melt from this magma ocean, it may be similar to the ultra low velocity zone. People have been arguing this may be partial melt. So this is a fantastic study that has been very influential in the community. So during my PhD, I also proposed a new origin for the LLSVPs that some of you may have heard about this. Yeah, unfortunately, this paper is still in review. It takes, yeah, everyone knows it's challenging to publish new ideas. So in this study, we propose actually the two blobs, LLSVPs, could be the mantle remnants of the moon-forming impactor Thea after 4.5 billion years. So I give a presentation in LPSC, Lunar Planetary Science Conference 2 years ago. The paper is still in review, so please stay tuned. Yeah, I hope I have another chance to present this work later. So in this main presentation, I will focus on two parts. First, what controls their morphology, and then how does their morphology tell us deep mantle flow? So as Luke introduced, I'm a geodynamist. I'm using mantle convection simulation to study how Earth's mantle convex. So we use supercomputers to solve three most important equations in our field. That's conservation of mass, and so conservation of momentum, and also conservation of energy. The code I'm using are mostly sitcom. In 2D, I use sitcom, and for 3D, I use sitcom CU. So then in this talk, when I talk about morphology, I'm specifically mentioning about the height of LLSVPs. Then why we care about the height of LLSVPs. Yeah, because the height of an object can tell a lot of information just by looking at the height. So this is a famous NBA player, Yao, that retired from NBA 10 years ago. You can see he's very, very tall. This is a famous golf. Kind of forgot his name. Yeah, I should better remember. So just by looking their height, you could infer or guess that Yao's parents are probably higher also than this guy's parents. Yeah, and you are right. Yao's parents are also professional sports and basketball player and volleyball player. They are very, very tall. So then from the height, you can kind of infer the inner property or gene character of the object. But also you may argue that to determine a people's height, the nutrition and outer environment may also play a big role in people's height. So this is kind of outer factors that may also influence the object's height. So whether these two, which one is more important, I think is still debated. So, but here I give an example that why we care the height of an object. Because by looking at studying the height of object, we can know the inner property and also environment associated with this object. Then we'll go to the blobs. What are the maximum height of LLSVPs? Previously, there are some regional studies. They either study this part of LLSVP or study this part of LLSVP. They are using different data set, using different research. So although the previous studies show the African LLSVP may be higher, but it's not very obvious. And also the height difference is a few hundred kilometers. And the resolution in global seismic tomography is also quite large. So in this study, we collected 17 global shear wave tomography models. We try to compare the height of these two LLSVP using the same data set, using the same definition. Because we think the LLSVP are dense thermochemical piles. So then if you have a cross-section of the LLSVPs, we expect the bottom will be cover a larger area than the top part. So in that way, because we mentioned the shear wave anomalies within blobs are slower than background mantle. So the DVS is negative. So the background is positive or zero. So if you simply get the average horizontal shear wave anomalies from the bottom to the top, you will expect there is a gradual transition because it's denser. When you will expect at the bottom, the average will be the smallest, as we can see here. But when you get higher and higher, the value will be larger and larger until you reach a turning point that may be the top of the blobs. Because when you reach that, you reach the background mantle, then it will be very similar. And then that average value won't be changed much, as we can see here. So we use this turning point to define the maximum height of the LLSVP for these cross sections. And then we can see we made many cross sections, like 30 of them. And then among these 30 cross sections, we found these 4 cross sections have the highest turning point for these 2 LLSVPs. And we can see here, the 2 red curves show these 2 curves for the Pacific LLSVPs. The 2 blue ones show the maximum height for the African LLSVPs. As we can see, it's very clear the top of the African LLSVP seems to be much higher, like 1,000 kilometers higher than the top of Pacific LLSVPs. Yeah, the higher African LLSVP is expected, but we didn't expect it to be that high. And also we did other methods, like we only use the negative shear wave anomaly, and also we use a cluster data published by VAD and Kota in 2016, also show similar result. But anyway, we are not seismologists. We are more interested in why there is a big, huge height difference between the LLSVPs. Then we use Mantle convection models to study 4 parameters, which are very important in geophysical field. One is the viscosity in the background mantle. One is about the viscosity of the pile. One is about the density contrast between the pile and the background mantle. Another is the initial volume of the blobs. So I show a reference model. It's very simple. As you can see, it's probably the simplest model in geodynamic field in the past decades. It's a 1-by-1 box. Here I show the temperature field. Here I show the compositional field. So initially I put a global layer to simulate the blobs at the bottom. As we can see in this simple model, when the cold downwelling starts to sink, and then this thermochemical pile or blob will be pushed to the right side of the boundary. If you run the case longer, it will reach a kind of steady state. In that way, we start to measure the height of the LLSVPs, of the blob. I shouldn't see LLSVP because it's models. Yeah, yes, as I mentioned, I run this case very long, and when it reaches a kind of steady state, we start to measure height. There is some variations, so we'll also consider the standard deviation of this height. So then in that way, we get the height for this model, yeah, when it reaches steady state. And this is a reference model. So using this method, we also explore other parameters. The reason why we put it that simple, because only in this way, you can measure the height very accurately. So first, we explore the effect of initial thickness of the piles. Here, I show these are from three different models. As we can see, initially they have different volume, 4%, 7%, and 12%. But when this case reaches steady state, you can see the height of them are very similar. This was also shown in the left plot. Here, the x-axis shows the initial volume of the pile, y-axis shows the height of the pile when it reaches steady state. So you can see, consider the variations, the height, initial thickness doesn't influence the height much. So the blue circles represent the 2D models. So yellow circles we confirm in 3D models. So they are similar. Of course, you cannot have larger volume. In that way, you will cover the core mantle boundary all the time. So that doesn't look like thermochemical power for the LLSVPs. If you have too less volume, then you cannot be stable. You cannot have a steady state. It will quickly mix with the background mantle. So the second parameter we study is the viscosity of the pile materials. Similar plot, the y-axis shows the height of the pile when it reaches steady state. The axis shows the viscosity of the pile. So from this plot, we can see, although there are some variations, yeah, but you can see that the variation is relatively small. And also we study a large range for the viscosity of the pile. So in that way, we can see the viscosity of the pile doesn't affect the height too much. Then for the other 2 parameters, which are very important. So one is about the background mantle viscosity. another about the buoyancy, which is about density contrast of the pile and the background mantle, between the pile and the background mantle. So in this plot, we can see if you have a higher background mantle viscosity, the viscous coupling will be stronger, then the pile will be higher, you can see. But as we can see, initially it grows higher, but when the pile viscosity is larger than some value, the increasing trend, it kind of slow down. It's not that much. But for the density, which is buoyancy number, if we are very dense on the pile, it's very hard to form a very high pile. But if you decrease the density of the pile, you can see it grows exponentially. Yeah, because it's very easy to understand. If the pile material is density becomes smaller, it will be more similar to the background mantle. Then it will be more unstable, and then the pile of the pile can be very, very high. So again, the yellow circles show the result for the 3D. It's also consistent with the blue circles. So among the 4 parameters we're studying right now, we found these 2 parameters are the most important factor to determine the height of a stable state pile. So after knowing this, we just did hundreds of calculations. So this plot is a little bit busy, so let me explain. So first, the x-axis show the background mantle viscosity. The y-axis shows the buoyancy number, which is density contrast between the pile and the background mantle, because we figure out these 2 are the most important factors. So 1 square here represents 1 geodynamic model. And the height of this, the color of this square represents the height of the pile in this case when it reaches steady state, which I showed earlier. So again, the blue color means the height of the pile is relatively small. When the color is red, means the pile in that case is very, very tall. And then we plot the seismic height of these two LLSVPs with constraint in the earlier part. In that way, because we mentioned the Pacific LLSVP is about 700 or 800 kilometers, then we'll plot mostly in this region, represented by the white star. For the African LLSVP is about 16 to 1800 kilometers, then we'll be plotted in this region. So as we can see, although there's a large gap, overlap between the background mantle viscosity, but it seems very clear that the Pacific LLSVP domain lies above the African LLSVPs. So that suggests the African LLSVP may be relatively lighter compared to the Pacific LLSVPs, because there is a density buoyancy gap between here. Yeah, this is interesting because I think before looks and our study, people all in geodynamic field, they treat them similar, call them LLSVP together. So this assume they may form similarly or have a similar chemistry and the physical properties. But my constraint is mostly from the height. Yeah, there's previous studies have been studied why African LLSVP is so high. There are 3 explanations about. First one, people will argue the height we constrain may include some mantle plume, because we know mantle plume have a close relationship with the LLSVPs. Then it's possible the height of LLSVP includes some mantle plume. But we are arguing that because there are also plume associated with the Pacific LLSVPs. Yeah, so in that way, it's maybe another very good explanation to see why explain why Africans is much higher than the Pacific LLSVPs, because the plume are associated with both of the LLSVPs. Another one is by another classical study by Underwell, published in Nature in 20 years ago. So in their model, they do real tank experiments. The pile can just rise and fall by itself, yeah, just by thermal evolution. But in their model, they didn't consider at that time the volume of LLSVP is still not clear. So they use a very large volume in their study, like 20% or 30% of them. And you can see the bottom of the pile seem to be connected together. Yeah, which yeah, may seem different than the two LLSVPs. But I have to say, this is a very interesting dynamic. That's still very interesting. Yeah, and also is shown by a real lab experiment. Another study by Tan and Gurnis in 2005. In this study, they assume that the pile have a depth-dependent buoyancy. So they suggest the pile have a different bulk modulus than the background mantle. In that way, the bottom of the pile is relatively less dense compared to the upper part. Then the pile can rise very tall, and the boundary can be very steep. So they use this phenomenon to explain the African LLSVPs. Yeah, but if this mechanism can explain the African LLSVP, there is also possible the Pacific LLSVP also have the different bulk modulus. So in that way, the Pacific LLSVP can also have this sharp boundary and also very tall. But actually, in seismic study, we only see that the African LLSVP is much higher than the Pacific LLSVPs. So then it's possibly, yeah, then we think our explanation that the two blobs have different density may be also another important explanation to explain why African LLSVP is so high, because they need to be different, such as the image I showed that the Yao's, the basketball player's parents is higher than another player's parents. So this property, their gene and inner property be different. So this is a very straightforward explanation, but we admit these are all possible. And also there is a Lux study published in 2020. Yeah. So also in this study, they collected the ocean island basal rocks that are related with two LLSVPs. And they compared their isotopes between these OIB rocks. Their results show that the ocean island basalt related to African LLSVPs include some upper continent materials in this region that doesn't exist for the ocean island basalt rocks related to the Pacific LLSVPs. So their studies suggest that subject continent materials may have incorporated into African LLSVPs. And we know that the continent materials are relatively less dense compared to the mantle and the slab. So then if you include more continent materials and didn't include that in the Pacific LLSVPs, this may make the African LLSVP relatively less dense compared to the Pacific LLSVPs, which is similar to our implications. And also a recent study published by Flement in this year in Nature. Also in their model, they show that there are more continent materials that are associated with African blobs. Although what's the depth distribution of that continent materials is still not well constrained in the lower mantle. Yeah. So I would say right now it seems our geophysical from seismic evidence and also geodynamic model agree well with the geochemistry study and also new geodynamic model. So in the last 6 minutes, I will switch my gear to talk about another interesting dynamic associated with the height of the LLSVPs. Because we mentioned in the early, the inner property of the height of the object influence the height, but also we say the environment also play a big role of the height of the object. So in our Earth, people assume there is a very strong dynamic change with the slab that's called slab avalanche. Because right now the seismic evidence show that between 660 kilometers and also 1,000 kilometers, there are many stagnant slabs that are horizontally distributed in this slab. But we know slabs are denser, so eventually this slab can sink to the mantle very quickly in a form of what people call slab avalanche. So we assume this process can produce a very strong heterogeneous flow that push the nearby LLSVP or blobs very, very high. Yeah. Instead of the mantle plume, we think this suddenly change of the force can push the nearby thermochemical dense pile to a very high place. So in our study, we only consider the phase transition from the ringwoodite when you transform to Bridgman and ferropericles, when this characteristic is negative, it can make the stagnant slab. But also there are many mechanisms can produce stagnant slab. But in this model, we only consider this mechanism just by include this phase transition as the steps. So here is a reference model. So this case initially is similar. We put a dense, this shows the compositional field, this shows the temperature field. Initially we put a global layer at the bottom. And then we let the model run. And this shows the phase transition boundary. So as you can see in our model, after 1 billion year, we can see because we have phase transition, the subtext slab was kind of stagnant in this boundary. Yeah. And also we can see at this time, the height of these two blobs are similar. But as we mentioned earlier, when you accumulate more subtext slab, it will become gravitationally unstable. So then there is a time it will suddenly penetrate to the lower mantle. And because of that, it can induce a strong mantle flow towards the bottom. And then it will separate this large pile into into two. And it will gradually push the left pile to a very great height. As you can see, this top of this pile almost reached the upper mantle boundary. During this whole process, we can see the height of this pile doesn't change much. Yeah, doesn't change much. And as you can see, this model in our model takes about 17 million years. In this case, we use a relatively smaller density. Yeah, otherwise, from our earlier work, we show if the density is large, you cannot have a very high, even though you have a strong slab avalanche. And the Clapperstone we use is negative 2.5, which is kind of not too large, not too big. But we also tested using a relative, even smaller Clapperstone. We still see this phenomenon. And the viscosity contrast due to temperature is 10 to the 5 order. So from this reference model, we can see that if you have a slab avalanche, it can produce a vastly different height. So also we have 3 kind of unsuccessful models. So here I only show the compositional field. The white color contour shows the subducted downweldings. Sorry. So in this model, the radian number is smaller than the previous reference model. If you have a smaller radian number, reference viscosity will be larger. In that way, the cold downwelding will be quite strong. In that way, the phase transition we use is not enough to stop this subduction. In that way, the strong subtext slab will easily penetrate to the mantle, and it will distribute everywhere. In that way, you will see the height of these blobs are all very similar. So in this case, we use a smaller buoyancy number, which is the density contrast of the pile. So we can see if in that case, this pile will be unstable, will be mixed with the background mantle. It cannot be stable at the core mantle boundary. In another case, we double the density of the reference case. So in this way, we can see the pile will cover the core mantle boundary, yeah, almost everywhere. Although you have a very strong subtext slab, cold downweldings, the separation of them are very, very weak and will quickly merge together. And also this volume and also it didn't form isolated piles that are like the LLSVP observes. So that's why we see this is unsuccessful. That means we didn't see that phenomenon we see in the reference case. But by comparing these 3 cases and also our reference case, right now we can know that in order to form a vastly different height of the blobs, you need 2 things. One, the inner property. The density of the pile need to be relatively small. Yeah, otherwise you either cover the whole CMB or it won't be stable in Earth's history. So you need to be a relatively sweet spot for the density. This is consistent with our first paper. Another one is that you need a heterogeneous subducted slabs. Because as we see here, if you have a strong slab everywhere, they are equally distributed in the mantle, then the height of the pile will be very, very similar. So this kind of give the answer for the introduction pictures. You need two properties to form a vastly different height of the two blobs. First, the density of the pile should be in a Swiss position, relatively small. Otherwise, you cannot form that high. Another one is that you need a heterogeneous subducted slab distribution of these subducted slabs. So now let's see the geological observations. So this is a figure modified from Facena in EPSL last year. So they make cross sections for the Earth. So again, this shows the seismic tomography for the equator cross sections. As we can see in this plot, the African LLSVP seems to be much higher than the Pacific LLSVPs. Also in their study, they did some viscosity inversion to calculate the mantle flow in the current Earth. As we can see, there is strong mantle flow pushing towards the African LLSVPs. This is consistent with some observations suggest there are strong seismic anisotropy associated with the African LLSVPs. But you may argue, in this plot, this figure also shows there is strong mantle flow pushing towards the Pacific LLSVPs. Why Pacific LLSVP is not that high? The reason we can think is that from our geodynamic model, we can see you need 17 million years to push the nearby pile to a very great height. So because there is some geological and seismic evidence suggests the subducted 30 step have already reached a core mantle boundary since about 150 million years. So these have enough time to push the African LLSVP to a great height. But when this cold down welding start to push the Pacific LLSVP is still unknown. So together we think this catastrophic thinking of stacking slab may cause a strong mantle flow to make a much higher African LLSVPs. So also I want to highlight this a great study by Zhong, and also I know Zheng Xiang is also the co-author. You see that the blobs and the supercontinent have a very close relationship. Yeah. So in this figure, if you don't have supercontinents, then it's a degree 1 mantle convection. The blue are cold down weldings. So these are cold down weldings, these are hot up weldings. But if you have supercontinents, you will form degree 2 structures. You will have two upper mantle, two up weldings. So whether the two LLSVPs, yeah, I think in the future, if I can also include more about the supercontinents, trying to study the height change in this dynamic coupling between the supercontinents and also the mantle convections will be very cool to study. So to conclude, two of my work suggest, first, the buoyancy number with density and also mantle viscosity mainly control the height of LLSVPs. And also we suggest the African LLSVP is probably less dense or perhaps less stable or perhaps less dense than the Pacific LLSVPs. Last, we think the catastrophic sinking of the stacking slab may lead to a much higher African LLSVPs. So if you are interested in the detail of these stories, models, please check these two papers. So there are some limitations for our work, as I mentioned a little bit earlier. So is that most of our models are 2D and some regional 3D. It's better to do some global 3D work and also include plate motion history, which is very important with the distribution of the subduct down weldings. And also another important question is that, has Pacific LLSVP risen significantly in the past? Yeah, this is a very big unknown, and also this may say a lot whether the two LLSVP have the similar chemistry from my geodynamic work. Although I already mentioned the geochemistry already show that two LLSVP are different in composition. But from the dynamic point of view, I think it will be very interesting to explore, or in Earth's history, has the Pacific LLSVP rising significantly? Because if the degree 1 and degree 2 structures, the super upwelling caused by the supercontinent can be mostly thermal. So in that way, so it may have the implications in that way. Because if Pacific LLSVP have never rise significantly, and also right now the seismic evidence already showed African rise significantly, so that can have a lot of saying whether the two LLSVP have different density, and also this can see a lot whether this LLSVP are mobile or not mobile. Particularly, I mentioned about the Pacific LLSVPs, which I think is very interesting and will be a highly interdisciplinary work in the future. So with that, I'm stop here and thank you all for joining this presentation.